Okay, so we'll look at one more example to warm up for 9-8. I think this is one you should be able to do. See if anything sneaky comes up. Try that one. So I don't need to, when you're doing absolute value for the ratio test, you don't even need to worry about that anymore, right? So you can write it in there if you want, and it still works.
Couldn't you just do the root test and make the ends cancel right away?
You could. I still do it with a ratio, I don't know. You can, totally. It'll work too. Do it that way if you like. It is kind of simpler, isn't it?
A little bit.
Because then you don't have to do this step.
Got your n on your x plus 1 on the right.
Oh. Thank you. Couldn't cancel otherwise.
Oh, you would have canceled it with the wrong thing.
Right. What do we have left? X plus 1 over 2. The same thing you get with the root test, right? You can see that one in your head with the root test, I guess. Smarter, Brenna. So I'm going to pull this 1/2 out in front. And oh, I kind of was a little bit not careful there, right? I got to make sure I keep that absolute value. That's pretty important because that determines like this whole idea of radius of convergence, right? So if you think about that, there's no n in there, so that just is like a constant repeated over and over and over again. So we get 1/2 times that constant, and the ratio test again says what?
0.
This converges if
Less than 1.
or it's less than 1. So now we kind of have this thing. What should I do next? I'd multiply by 2. You can do it however you like. So that's less than 2. So if you think about that on the number line, what's that look like? If that's 0, where's this guy centered? -1. And you can go back up here and look if you like too. The center's -1, right? So I don't know. However you like to, it should all fit together. And then we're going to go 2 away from. Remember, the way to read this is that's the interval centered at -1. You go out 2 from that center, because that's what absolute value means, distance away from 0, or in this case, distance away from -1. So you go out a distance of 2 in both directions. So that's what, -3. And then we have to check our edges, right? So let's think. If we put -3 in, what are we going to get? We're going to get the series.
1 to the n times -1 to the n.
Like an alternating
That's
geometric series.
negative
R
1 to
equals
the
1.
2. And
Isn't it -2 to the end? If you put you're putting -3 in, right? That's the edge. So right now, this guy goes from here to here. We know all those things in between converge, but we're not sure about the edges. So -3 is going to make
it's
this
the
be.
same exponential, so it can just be -1 to the n. Because you can do -2 over 2 to the n.
Okay. I'm too slow. You guys are faster than me. So these are all to the n, right? So couldn't we just go, you guys put these together because they're the same base, but you could also just go, what, 2 over 2 to the n, because that's all inside.
So that diverges.
That's 1 to the n, which is the series of 1. which diverges because it's 1 plus 1 plus 1 plus 1 forever. So it's going to keep growing and growing and growing. So that's going to stay open. What about if we put 1 in? Then we're going to get the series. I should label this clearly. So that's if x is -3. What if we put 1 in? So we're going to get -1 to the n and 2 to the n, 2 to the n. Those just cancel. We get the alternating series -1 to the n from n equals 0 to infinity. Ooh, what's that do?
Converges.
You sure?
Yeah.
It's that, right?
Mm-hmm.
Because at infinity, you don't know if it
Plus
should
or
be
negative.
0 or 1.
So can we apply the nth term test to say that specifically then? So the limit as n approaches infinity of the sequence is plus or minus 1, which is not equal to 0, so it does diverge, doesn't it? I keep thinking that that one's going to converge, but this one doesn't diverge because it's like growing off to something or shrinking down to some negative
Doesn't settle
infinity.
down to 1.
It's because it's a bouncy one, which is not as common in series, right? Sequences are pretty common for them to bounce around at the end and oscillate. Series don't do that very often, but this one does. So, let's see. So I guess that's it. So I guess our interval of convergence on this guy is that. Okay. Let's see. So I think all we have left to do is, why don't you guys look at page 664. I'd like you to just kind of glance through that. You can read it in more detail if you need to. I'm going to give you the gist. You guys can see if you can tell me the gist first, but definitely read page 664. Got a little bit of history in there. It's kind of nice. Then we'll talk about the gist. Just is pretty bad language, I'm going to say. Let's distill it down to its basics. Anybody summarize what that page says yet? It's pretty technical, but actually doesn't say anything too hard. So it's crazy, like we're doing this in calculus class, right? But if you look to the left hand there, it said who invented this idea, or who was working with this idea, kind of credited for this math. guy named James Gregory. And what are his dates?
Before Newton.
He was before Newton. He was a contemporary of Newton. He was older than Newton, for sure. So he was developing this stuff before Isaac Newton. Crazy, huh? So people developed a lot of the pieces of calculus without having the main idea. Newton's the one who put all those pieces together and then also developed a whole bunch of new pieces on his own. That's kind of the way research goes a lot of the time. You know, people are shooting in the dark, kind of. There's a picture out there that's a whole picture, and this person shoots this ray and gets this little piece of the picture, and it's kind of right. They're not really sure why or how exactly it works and stuff, right? And someone else shoots and gets that part of the picture, clear on that part, but they don't know how it relates to this other guy, and then take somebody really courageous and intelligent to come along, someone really clever like Isaac Newton or Einstein, just totally pull back the curtain and say, oh, these things were all really just little parts of this big machine the whole time. Nope, nobody can summarize.
When you take the derivative or integral of a power series, it's basically like taking the derivative or integral of each term.
Yes, there. Paul said it well. He said if you take the derivative or integral of a power series, it's just like doing it kind of term by term. Totally true. So I said this. I said you may differentiate and also integrate a power series, and this is done by people for lots and lots of different reasons. You can only do that really on its interval of convergence, which should make sense because remember, a power series is just a function and its interval of convergence is its domain, the only place it makes sense to think about that function. So think about a function like if it has an asymptote. If it has an asymptote, can you take a derivative over that asymptote? No. Can you integrate over an asymptote? No, we did learn how to like integrate up to the edge of an asymptote using improper integrals, right? But we never actually like just ignored it and went to both sides. Like that causes mistakes and it's just wrong. So, but you can do it on its interval of convergence. A key thing is, which I think was mentioned on that page, is that the results of that process, whether you take a derivative or an integral, the results come out to be the same interval. So I'm going to say being applicable to the same interval. So once you've taken the derivative or integral of power series, it applies to the same interval except the edges might turn out to be different. Okay, so we're going to say except possibly at the edges. But otherwise, I mean, this is not that big of a deal. You just integrate things term by term, you differentiate things term by term, you get your answer, you check its edges over again, done deal. And you know how to take as many derivatives or as many integrals, go as far forwards or backwards in that process as you need to go. Okay, so it's not that big of a deal. Let's look at a couple examples. I think I'm just going to take the book's examples. So example 8, they said this is a power series from 1 to infinity, a pretty basic one centered at 0, just divided by n. Okay, so you could even think about what that power series is if you write out a few of its terms. Right, that's the power series we're thinking about. And the whole concept for this is to take the derivative. What would the derivative of this whole series be? Well, the first term in the derivative would be 1, and the second term in the derivative would be x, and the third term in the derivative would be x squared, and the fourth term in the derivative would be x cubed. See how it comes out kind of nice? Interesting. But let's do it like all at once. powerful way. So let's find f prime of x. So if this is f of x, the function, we should probably, actually, before we find f prime of x, that's not going to be a big deal at all. What should we check about f of x? We should figure out where the domain of that is. Yeah, we should figure out its domain first. What's its interval of convergence? Can we do that without even writing down the ratio test? Can you do it in your head yet? For an easy one.
I'm thinking radius is going to be 1.
Yeah.
Centered at 0.
You guys see that too, or no? It's on the edge of my ability to do. Well, I guess we can write it down really fast.
It includes -1, but not +1.
Good. Right? I guess we'll write it out really fast. So what's that limit? Good? Yes or no? Okay, so then Paul said, which for the original series, if we put in -1, we're going to get the alternating harmonic, which converges or not? Alternating harmonic converges, so I think we can go like that. And if we put in 1, it's just the harmonic, which diverges, right? So we know the interval of convergence is that. Good? So if we're going to take the derivative, how do we do that? Well, don't think about this so hard. Make it easy on yourself. I mean, you're not doing stuff that's rocket science here. People might look at these symbols and be like, oh my gosh, it's so intimidating. But it's really not. You just go, okay, well, how's the derivative of that go? You know how to take a derivative of something like that. Don't you pull the power down? That's what you did when we did it term by term a second ago, right? And then you decrease the power by 1. And oh, this part doesn't have an x on it, right? So when I'm doing f prime of x, I don't have to worry about that. That's like a constant, isn't it? So when I'm doing f prime of x, it's like there's an operator d dx going in here, and it's just touching the x parts. Everything else is constant. That's a really key idea. See, that's what's going to let us be able to jump into Dr. Lundberg's Calc 3 class, is because that's the only concept we really need for Calc 3. Like, otherwise, we're good. So we'll see how that concept goes a couple days. We'll be ready, I think. We'll see. We'll see. We'll see. We'll see. So what is that? Chop, right? So we've got n equals 1 to infinity. Get rid of this. It's distracting me. X to the n minus 1. We already know that that guy is going to converge on the same -1 to 1. We're just not sure about its edges, right? So this guy we already know converges. You could do it out again if you wanted to check, but it's going to work. I really just need to check x equals 1 and x equals -1. So at 1, I get the series 1 to infinity, 1 to the n minus 1, right? Is that going to converge or diverge? I think we just talked about something like that. It's going to diverge, right? It's going to alternate. We just talked about that one. So that guy diverges. Same reason as a second ago. This guy, same thing, right? It's just going to be -1 to the n minus 1. This isn't going to alternate, though. I'm wrong. This guy's just going to be 1 plus 1 plus 1 plus 1. This one's going to be 1 minus 1 plus 1 minus 1 plus 1. So this guy diverges. Let's put plus or minus 1 there just to be a little bit. Put something here. There we go. A little bit explanatory, right? Okay. So the derivative didn't match, did it? Derivative's interval of convergence is open on both sides. And if we're going to integrate, how would that look? Well, think about it just like James Gregory would have thought about it. If you're going to integrate this guy and you integrated it, what would like the first term be? We did it term by term.
X squared over 2.
And the next term would be
X cubed over 6.
and the next term would be 4 times 3, 12. Okay. Just checking. 20. So there's the integrated series. Technically though, I didn't do one thing right. I forgot something pretty fundamental to integration. Each one of those would have its own plus c on it, and then you could just absorb all those plus c's into a c. Where do you think you want to put the c? Over here? You don't want to like shove it at the end of all those terms, do you? Shouldn't it probably be right here instead? That kind of makes sense more, right? The constant would be up in front instead of like with x to whatever power down there. So if we integrate it all at once, let's see if it kind of matches up. So if we go, what's a symbol I could write down if I want to integrate without writing a little integral? Kind of like this. Or you can go like this. I don't like this because then I'd have to put a dx here, and that dx kind of isn't part of the notation, so I prefer this actually. But you make the notation work how you like. Anyway, so how's this going to go if we go from right here? It's going to go series x to the n plus 1 divided by n times n plus 1. There we go. It's not too hard, is it? I mean, if you want to check that that's right, see if this matches. Plug in 1. If you plug in 1 for n, right, you get x squared over... Do I have a mistake? So you get x squared over...
2
times 2 is 2. Okay. I cannot do basic arithmetic today. I'm sorry. My class hour screwed me up or something. So it's working. Man, that's bad. Okay, so we know this guy's interval of convergence already is at least what?
-1 to 1.
-1 to 1, but we've got to check the edges. So if we do that edge, we're going to have this series which is really just this, right?
Yeah, and you can just compare that to 1 over n squared.
Yeah, so should we do a direct comparison? We can probably do either kind. Let's do a direct comparison. If we go, this guy, is that guy always less than that?
Yes.
Definitely, right? Its denominator's bigger, and this guy's convergent by P series. So this guy's definitely going to converge. So check, got it. And then we want to check -1. So for -1, we're going to have the series -1. Just checking, yes. N+1 n times n plus 1.
Just the alternating series does that. I think
We could.
it's always decreasing.
It's always decreasing, right? Like we don't even need to think about it. We can just look at this guy. I guess we could write it down though. What would it be if we find, what is it? N plus 1 times n plus 2
Less than 1 over n times n plus 1.
over n times n plus 1. Clearly that denominator is bigger. Check. I guess we could write the limit as n approaches infinity of 1 over n times n plus 1. Clearly 0, check. That converges. I'm getting really sloppy here. Converge by alternating series. Okay, so what's the interval on this one? It's going to be that. So the original series was open on one side and closed on the other, right? Like this. Derivative was like this. Integral's like this. but otherwise they have the same convergence. Okay? So I think that's the main idea. That's it. Let's see, do I have anything else? Ah, one other thing. You guys read 664, right? There's something really, really key. It asked you a question at the bottom of the page. You guys see that? You recognize this function? So what did it do? It said, it gave you a power series, it just had it expanded, right? Like term by term. What was the first series?
X to the n over n factorial.
So f of x was a power series that came out to be 1 plus, let's write it in expanded form, x plus x squared over 2, is that it? Plus x cubed over 3 plus, this is the one we started out with today. And then we took its derivative, and once it's derivative, well, you can do it term by term. 0, 1 plus x plus, I guess I'll write it out for anyone watching the video. So that'd be like 2x over 2 plus 3x squared over 3 plus 4x cubed
The
over
denominators
4.
are factorials.
Sorry.
Which would be
What's up?
the denominators of 3 and so on are factorials.
Am I looking at the wrong one?
So it just
Oh,
adds
yes,
the
this is
3
the
and
factorial
leaves
one.
2 factorial.
Sorry. So this was what? So the series that we were looking at here was not x to the n over n, but over n factorial. Is that it? Yeah. So this should have been. So how do I fix that? X, right? Because 2 factorial is 2. 3 factorial is 6, but you could even write it as 3 times 2 times 1. So you could get the 3's to cancel and have plus x squared over 2 factorial. And then here we'd have 4 times 3 times 2 times 1, so the 4's would cancel, and we'd have x cubed over 3 factorial plus. Look at that. It's the exact same, right? So this function, whatever it is, f of x is equal to f prime of x completely perfectly. So my question to you is, the power series right here, what function is that? Only one function has that property from your library.
dx.
E to the x. So when your calculator does e to the x, your calculator doesn't know those infinite values. It just says, hey, the power series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and it probably goes out to like x equals 15th power. Maybe even not that far, probably. Factorials go really fast, right? That might strip it out. So maybe even just x to the 10th power would be good to try, wouldn't it? You could probably play with our calculator and see this. And it just cuts it, and it says, well, if it's e squared, I put 2, 2, 2 in all those spots. If it's e cubed, I put 3, 3, 3. If you put 1.7, 1.7, 1.7, 1.7, 1.7, and it can do that. That's how your calculator does everything. So, pretty neat. Should we try it?